Good. Our next speaker is Gabriele Lobbia, and his talk is entitled Finitary Definitions of Multicategory. Please go ahead.
Thank you to the organizer to organize this conference in such difficult times and for letting me speak. Today we'll talk about finitary definitions for multicategories, which is a joint work with John Burke. And the first thing that I have to say is that the title is a bit of a lie, because actually finitary probably is not the right word, so I'm warning you. Maybe finite would be better, but I will explain what I mean, and hopefully it will be clear. So the picture is the following. So we've got these three characters. We've got monoidal categories, which are categories equipped with tensor product. Then we got closed categories, which are categories equipped with an internal hum. And then our main character multi-categories. The nice thing about this picture is that we got a lot of different equivalencies between different flavors of these three characters. For example, we got an equivalence between representable multi-categories and monoidal categories. Then we also have an equivalence between left representable multi-categories and skew monoidal categories, which are left normal. And so, yeah, we've got a lot of equivalencies. And the good thing is that they all have some pros and some cons. And so having these equivalencies, you can switch between them as you want. Let's see the good things about, for example, monoidal categories. So the good thing is, and now I will explain what I mean with finitary and infinitary, is that we've got these two definitions. We've got the usual one, where we've got a binary tensor product. We've got associator, unit, and a finite number of axioms. And I mean finitary because we've got a finite set of things and finite axioms. And instead, we've got this infinitary, which is, again, used probably wrongly, but I mean the unbiased definition, where we've got an infinite number of products, and every product for every n, and then an infinite number of associators and infinite number of axioms. And that's good because we got both of them, but the problem is that usually the tensor has got a not super nice and direct definition, because usually it's a colimit. Whereas, for example, closed categories is really nice that we've got hums, and hums usually have a nice definitions. Like hums usually are maps equipped with a structure. So they are usually a bit more explicit, but the problem with closed categories is that working with iterated hums is a bit like hell, because it just gets a bit more complicated, and you would like to avoid doing that. Finally, our main character, multi-categories, the good thing about them is that we don't need either limits or colimits, but we only use universal properties. Think, for example, about multilinear maps in this sense. And the problem instead was that we didn't have a finitary definition, but we only had an infinitary definition, meaning we had to define an infinite number of maps, a set of maps, infinite number of substitutions, and checking infinite number of axioms. The aim of this talk is to show that both multi-categories and also skew multi-categories sometimes have a finitary definition, meaning we can define a finite number of multi-maps, and we can check finite number of axioms. Let's go. Let's revise a bit classical multi-categories. So let's see the usual definition. So the idea of multi-categories is that instead of having objects and then morphisms from one object to another one, we've got objects and then morphisms with more than one input and one output. So we will have a collection of objects, and then we will have, instead of just one set of morphisms between two objects, we will have a set of n multi-maps for every n. And then obviously we will also have an identity, which will have to be a unary map. And then we need to do something similar to composition. But again, here we've got maps with more than one input. So what we have is a substitution operation, which don't be scared about the weird equation, but the idea is that you can take a map with n inputs, and so instead of just pre-composing it with one map, you can pre-compose with n different maps. And then obviously we also require some associativity equations and also identity laws. So this is the picture. Now we will see an alternative way to phrase what a multi-category is. So instead of starting with object, we just start with a category, because if we consider a multi-category and we just consider unary maps, we get back just like a normal category. So we will start with that. And then for multi-maps, we will consider profunctors. And in this way, let me notice that this profunctor structure will already give us the precomposition and postcomposition with unary maps, because that's just what the profunctor action gives you. And obviously we were required that for n equals 1, we get back the maps in the category. Then, instead of the substitution that I described before, we just consider these special substitutions, which are the one where we just precompose with one map into the if component in the if input. And we will call them circle eyes or whatever, and they correspond to this equation that we can see here, where exactly like we precompose with all identities except in the if component. Then the nice thing about phrasing it with these circle eyes is that we can phrase the associativity equations in this quite compact way in 2 different equations. Don't worry if you don't understand what kind of equations they are. In the next 2 slides, we will see examples of them to understand which are the 2 possible conditions that we encounter. And just a quick remark, starting with these circle eyes, we can get back the definition of the substitution that I said before, just like doing 1 per time. And the second equation here says that it doesn't matter the order where we do these circle eyes. So let's quickly see some examples of these associativity equations. So one of them is when we got 3 in a row, and we do f into g and g into h. And then obviously we've got two different ways to compose these 3 guys, and we require them to be the same. The second case of associativity is where we have g and f into the same map h. And we can do g before or f before, and obviously we require them to be the same. I show this second alternative definition because it will be the one that I will use as like the format for my definition of a finitary multi-category, and it will be this one. So we will start, as I was saying, with a category, and then we will basically do the same, but stopping at dimension 4. I mean, with stopping at 4 multimaps. So we don't require profunctors for any n, but just up to n equals 4. Then we require the substitutions, again, the circle eyes, but not all of them. We require some of them, which ones? The ones that give us something that is maximum of dimension 4. So for example, we won't have something like a ternary map into a ternary map, because that will give us a 5-area map, and we don't have that, so we don't want that. In particular, the ones that we will have are binary into binary or ternary, ternary into binary, and then nullary into binary or ternary. Let me just notice that, for example, we could also have had nullary into 4-ary and get a ternary map, but actually we don't need that for proofs, so, well, we just don't put that. And then the associativity equations are literally the same, but of course we don't have all of them, we just have, I think, around 10 of them, because like f is always binary, g in the top one is always binary, in the bottom one could be binary or nullary, but yeah, like you can write them down, there are not that many, and they're just, yeah, around 10. Now, let's go to the theorem. So as I was saying, we don't always have this finitary definition, but we do have this finitary definition for some cases, for example, for left representability. So let's define left representability, and we need to start with a classifier. And a non-array map classifier is just a multi-map, an M multi-map that induces these kind of bijections. So basically, it's a multi-map classifying n multi-maps from this list, and so on. Then to be left representable, this is not enough, we need more. And left representability is when the bijection stays bijections when we add something on the right. left, I guess, because the product is on the left. It doesn't seem like an important condition, but it is. It's very important, and even like representability would be if it will still be a bijection adding something on the left of M, and that's even more. And like we can see that because, for example, representable multi-categories are equivalent to monoidal categories, but if you just take left representable multi-categories, you get skew monoidal categories. So you get like way less. And we define a finite multi-category to be left representable if it admits a left universal nullary and binary. Again, just these two, because the point is that starting from these two classifiers, we can actually get a free array classifier composing them in this way. And here we are using left representability a lot because we are putting C on the right. Like it wouldn't be the same putting C on the left. So here we are using left representability strongly. And now the idea now is that we want to prove that our finite definition, so finite multi-categories, will be equivalent to multi-categories, left representable in this case. And to do that, we go a bit around it and we try to prove an equivalence with skew left normal monoidal categories. And so our aim is to construct a functor from the category that you can define adding morphisms of finite multi-categories and the category of skew monoidal left normal. And here again, left representability is crucial because to define alpha, for example, which is a map from AB times C into A times BC, since AB times C is universal, we can just, alpha will correspond to a ternary map from ABC into the right object. And so we define alpha to be the only map satisfying this equation. And similarly, we can do with the units. Okay, let's go to the theorem finally. Our theorem states that left representable multi-categories are equivalent to finitely left representable multi-categories. And the way we did it, as I was saying, is to factorize this equivalence that was already done by Burke and Luck between left representable multi-categories and left normal skew monoidal categories. And yeah, the strategy is just to prove that K, to define K, first of all, prove that K is fully faithful using some characterization, and then K is also essentially surjective because the diagram commutes quite easily, and therefore U is an equivalence. But it doesn't end here because we can also add closeness. Closeness means in multi-categories means that we've got these isomorphisms. Basically, the idea is that you can reduce the dimension of n multimaps, n+1 multimaps using these sort of internal homes, which are not really internal homes. And the good thing is that the equivalence that I described before induces an equivalence with if you add closeness to the equation. So if you have left representable closed finite multi-categories, you get an equivalence with left normal skew closed monoidal categories. For those of you who are interested in this, you can also do the same just with closeness and go to closed categories. Let's go skew now, finally. Let's revise first what a skew, we will revise what a skew multi-category is. If it goes on, it's not working. Okay, we will revise what a skew multi-category is, and then we will define the Finitary one, which will be similar, and the result will be the same with skew in front. So skew multi-categories, they are similar. The structure will be similar, obviously, to multi-category with something added. So we will have objects, nuller maps, and then instead of just one set of multi-map, we will have two sets, one of tight maps, one of loose maps. And I will explain how to interpret this, but let me just go on for a bit. First of all, we want to see tight maps. We want to be able to see tight map as particular kind of loose maps. And we do that with sort of inclusion, which doesn't need to be an inclusion, but usually is an inclusion. Then we want, obviously the identity, and the identity will need to be tight. Can make sense even from the name. and then the substitution operation. But since we've got two kinds of multi-maps, we need to describe when this substitution operation is tight and when it's loose. And the rule is that the substitution is tight if only if G and F1 are tight. We will see why this is the case. Let me just underline the fact that nuller maps, they only have one kind and they are labeled L. And again, next slide, we will see why. Obviously, associativity and unit axioms will also be needed. Quick example, the category of categories with a choice, and important being a choice, of finite products. And here the multi-maps will be maps from the product to the category, preserving products up to ISO, and these will just be loose multi-maps. The tight one will be the one strict, so preserving strictly the product, the choice of your product, in the first variable. And that's exactly what is the idea that you have to have of tight maps. Tight maps will need to be, you need to think about them as things that are tight, they are strict in the first variable. And for this reason, you can see that if G is tight, so it's strict here, and F1 is tight, then the first variable will still be strict in some sense. And this is the rule of substitution. And the reason why nuller maps, you have to consider them as loose is because if you substitute a nuller map into a tight map, then you lose the first one. Then the first variable becomes the second one of F, and F was tight in the first one, not in the second. And so that's why nuller map, you have to consider them as loose. Let's just quickly see the Finitary definition. The Finitary definition would be similar with a bit added. So with tight maps, we'll have from 1 to 4 because nuller maps are only loose. And yeah, just let me notice that here, the map, so we start always with a category and the morphism of the category will be the tight unary maps of our multi-category, not the loose ones. Then we will need to define also loose maps, but luckily we just need nullary loose maps, unary loose maps, and binary. We don't need actually ternary or Fourier, which is quite nice because usually loose maps are a bit more complicated. And then we want J for just the ones that we have in common. And then substitution functions, again, we will need to add a bit more from the normal case because we also need some loose unary substitution here and there, but it's not too much more. And also with the axioms, associativity is basically with tight maps, so still nice, except that we need to add an axiom also for compatibility of J with some substitution, but not much. So basically the idea is the same with a couple of axioms more. Then the theorems, as I was saying, they're literally the same as the normal case when you put skew in the front, because luckily Burke and Luck did a really nice job of having a lot of different equivalencies. And so using them just the way I explained before, we can find, like we can prove that our Finitary definition works also in these cases. Do I have time to go on? Because if I have time, I got a bonus track, which is about bi-closed multi-categories. And then bi-closed, so when I was talking about closeness, I was actually talking about left closeness, which is the isomorphism at the top. So when you have a norm that goes and the other object goes on the right. So you take the last one and it goes on the right. Instead, right closeness does the opposite, like takes the first one and it puts on the other side. So bi-close is when you've got both. And the nice thing about bi-closeness is that you don't even need to define the circle eyes because you can define the circle eyes using these isomorphisms. For example, if we start from a binary map and want to substitute it into the middle of a ternary map, we can use lambda and rho to make G a unary map from B2 to something really awful. Then by proof to reality, we know how to compose this binary map F with this unary map. So we do that, and then we obtain a binary map from A1, A2 into, again, awful thing, but then the awful thing, going back with the reverse operations, basically, we can make it, again, at this point, a 4-array map from B1, A1, A2, B3 into C. So in particular, you can do it generally with this big diagram where the red part is a composition of the lambda and rho. That was the first part of the description. Then you use the profunctor action, and then you do the opposite. And so finally, we can just, the nice thing is that you can describe bi-closed multicategories just as a list of profunctors and some equation, profunctors, isomorphisms, lambda and rho, and some extra equations about lambda and rho, which are not amazing, but you can, like, once you get there, you can change them to the associativity equations from multi-category, and maybe they look a bit more nicer, but you still can define this way, which is, I guess, nice. That's it.
Great. Comments or questions? Let's see online. Alex, you have a question.
Hi, great talk. I hope you can hear me. So I'm tempted to ask, how about the symmetric case? Do things simplify even further, or perhaps get more complicated, or what?
So the braided and symmetric case, I mean, you need to add a bit of structure. I believe it's possible, and I believe it would be nice because of the the fact that you only need nullary, unary, and binary. So actually, the braided case, I think it's interesting. We still need a bit of time. We talk about this. We haven't proved anything yet, so we're not sure it works. I believe it does, and I believe it would be quite nice because, again, you don't need many loose maps. And that's in the definition of a skew braided multi-category, makes things quite nice. And then symmetric, you just rearrange it.
Great. Any other comment or question? If not, then let's thank the speaker again.